Hi. So yeah, I'm going to talk about regulation, but I'm going to talk about it in the context of high redshift galaxies. And what I'm actually going to talk about is high redshift clumps. So Yu Cheng actually set me up perfectly for this on Monday. So we have all this wealth of data now. We have this really awesome data from candles, right? And it tells us that clumps are large, on the order of a kiloparsec maybe. Recently, we have this really interesting lensing reconstruction data from a group at the University of Michigan. So they get like 30 times magnification in their galaxy, and they can find very, very small clumps. So I think their biggest clump is on the order of 100 parsecs. So granted, these are two very different samples, but we have very different results. And if we look at simulations, we again see this dichotomy. So this is from a NUI 2016. We know that they get very large clumps like candles. Valentina Tamburello has done work where she gets smaller clumps. And Berendt, who's a student of Andreas Burkert, has shown that if you have small clumps clustered together, smear it to the resolution of HST, and they can look like very large clumps. So we have all of this data, all of these different samples, different galaxies, and we're getting to a point now where we're starting to wonder, how should we piece it all together? Are clumps big? Are clumps small? Are they both? So being interested in this problem, we decided to do isolated galaxy simulations to see if we could study this in sort of a controlled way. So we did 3 galaxies. These are stellar maps of them here. Oh, I did something. Okay, fix it. So the first one was a gas-rich galaxy all by itself. The second was a less massive galaxy that had a weak interaction with a companion, and then that same galaxy having a strong interaction with a companion. And you can see that you form nice big stellar clumps. But what we found was that when we went to analyze these, we just wound up more confused than we were before. And the reason for that is when you have an isolated galaxy, evolution happens so rapidly. So when you're looking for things like the clump mass spectrum, or we were specifically interested in clump formation signatures and predicting where they were going to form, when that evolution happens so quickly, it's really difficult to untangle the clump origins. So it's like being brought to a pile of rubble and being asked what the house looked like, knowing nothing else. So it was at this point that we decided to go back to the drawing board and see if we could think about a different way to come at this problem. So I think what we're all really looking for is a theory of fragmentation, right? And that's intimately tied to turbulence. And Nir told us about that on Monday as well. So you could ask questions like, is there a special scale for fragmentation in a galaxy? People have thought about this a lot. So Oscar Egerts has done some work coming up with scale-dependent formulation of Q to see if there's a special scale. Phil has done work on this, looking at scales of turbulent fragmentation. The tricky thing about turbulence is that it's difficult to resolve. So Alexei Kritzik tells us that we need 512 resolution elements across our scale of interest to resolve generation of turbulence in a simulation. And that's a lot. Granted, this is very conservative, but this is really difficult. We know there are methods for getting around this. Vadim has told us about this. But I'm going to do something even simpler to try and get around this. So what we're going to do is we're going to pose similar questions. Is there a preferred scale of fragmentation? Is there a most likely clump mass in a given galaxy? But we're going to go at it from a different angle. So we're going to seed perturbations ourselves in simulations and see what happens. And in this way, we avoid having to resolve turbulence to generate the perturbations itself. So that's what we've done. We've done a suite of isothermal simulations where we go in and seed perturbations. And we seed these perturbations on different size scales and with different magnitudes, so different velocities. So the disk that I'm going to talk to you about today has a gas mass of 6.9 by 10 to the 9 solar masses. That is small if you're comparing it to like a gas-rich high redshift thing, but we have more massive galaxies. They're coming. Everything will scale up that I'm going to talk about today. We did this with the simulation code gasoline. And as I said, the perturbation sort of space we explored were velocities on the order of 1 to 20 kilometers per second and sizes of 0.25 to 5 kiloparsecs. Close, yes. We have 10 parsec softening. I can't hear you. You ask later, yeah, okay. So here's an example. We have 4 cases here, okay? We have a case on scale 500 parsecs all the way up to 2 kiloparsecs. And so what you do is you introduce your perturbation and see how it evolves. So the first thing that you want to ask is, what does the space of success versus failure look like? Okay, so here are some samples that I've thrown up for you here. Here we have varying the velocity and then varying the size scale of the perturbation. And these are zoom-ins 1 kiloparsec around the perturbation, and you can see this is a surface density projection of the gas. So you can see first off, there are cases that don't form an object, right? Sometimes you get a ring, sometimes you don't get anything at all, and these happen preferentially at small scales or at small velocities. But then there are cases where you do form things. So here you can see clear cases where you form something massive at the center. And this extends, I wasn't able to include it, but there are cases over here where if you go too big, then you wind up being limited by shear and you can't form anything. Okay, so this is great. So what we want to do next is identify clump masses. So in an isothermal simulation, I haven't done star formation, but what you can do is you can go in after and you can post-process, and you can tag star particles by saying if gas gets above 100 solar masses per parsec squared, then it's a star. And this is motivated by Charlie Latta's extinction criteria. Once you have the stellar map, you can track clumps using, we use AstroDendro, which is a tool that finds structure based on dendrogram trees. So here's a sample image. You have what the gas map looks like. This is a surface density projection. And then you have what the stellar map looks like. And AstroDendro finds an object in the center, and its mass is 7 × 10⁶ solar masses. So then you can go and you can do this for all the cases that we're able to form something. And you can come up with a space for the range of masses at different scales. So plotted here is that stellar mass as a function of the scale of the initial perturbation. And then the different symbols show you different velocities. So you can see some general trends. For instance, as you increase the size scale, your masses tend to get bigger, although there is turnover. So this will turn over if you keep going. And you can see the open circles are cases that weren't able to form anything. So you can see, again, preferentially, there are scales that form nothing, and there seem to be scales that are very successful at making objects. So for instance, nothing fails at 750 parsecs. Okay, so this gives us the range of scales, and it tells us that there seems to be a preferred mass around 5 × 10⁶ solar masses. But what we really want is the most likely mass in a given case. And we can get that. All we have to do is make some assumptions. So the first thing you do is assume a form for the turbulent spectrum. So we're going to take this from Kritzuk. So we assume the turbulent spectrum is sigma goes as L to the half. This is actually just Larson's law. Then you choose a normalization for that. This is, of course, galaxy dependent. So for my smaller galaxy, I'm going to say sigma naught is 10 kilometers per second. And if we assume that that turbulence is generated by something like superbubbles, then you assume your generation scale is 1 kiloparsec. And that gives you the spectrum. Once you have the spectrum, you can assume the probability distribution is Gaussian, and you can get the probability of any one velocity at any of your length scales. Then what you can do is, you have a discrete set of masses at each velocity, and you can convolve those two together. And when you convolve those together, you get the most likely clump mass at a given scale for a chosen galaxy. And that's what that looks like. So what I've plotted here is, again, that mass as a function of the initial perturbation scale. Now the dotted line shows you the most likely mass at any scale, and the gray region shows you the 1 sigma around that. So there aren't that many points on this plot yet. Like I said, more galaxies and many, many more conditions are coming. So I encourage you to stay tuned. This is very preliminary. But I think this is really interesting because what it can tell us is that while maybe you can form something very massive or you can form something less massive, it may not be the most likely thing to form in a certain galaxy. And we can combine this together with what we know about which scales are successful, and you could imagine pulling out one mass. What is the most likely mass in a given galaxy? And you could look at that in both simulations and observations. And I think this could be a really interesting tool for now helping us put all the pieces of the puzzle together. So with that, I'll just leave my conclusions up. Thank you.
So you really want to know the mass and the scale that you're talking about in terms of the turbulent mass. that is relevant for this test?
Mm-hmm.
Do you tell us?
Not off the top of my head, no. But I can calculate it for you.
I mean, that's the question.
Yeah, is it consistent with TUMRE, you mean? You mean the question is it consistent with the prediction from TUMRE?
Yeah.
Yeah.
How is it?
So I mean, these disks are all initially TUMRE stable, though. The disks are initially TUMRE stable.
Yeah, 1.4. The question is whether the scale is comparable to Thomas, which is also the D scale.
Hmm.
So do you have more mass cases?
Yeah, I do. Yes. Yes. So that's coming.
Related to the starvation rate, you assume some simple.
Yep. So like that's all you do. So I assume a surface density threshold. So you just bin the gas particles, and anytime a bin gets above 100 solar masses per parsec squared, you say there would have been star formation in that bin, and then you can tag those in their stars as you go forward.
You don't bother with things like dust.
No, not at this stage, no.
Okay, let's thank Samantha again.